Yeah, okay. So the next talk is by Gilles Bellon from CNRM.
Hello, everybody. I'm very happy to be able to join you today. I was tasked by Vishal to give a little presentation on uh, hierarchy of monsoon models. So by hierarchy of monsoon models, we think mostly physical or physically based monsoon models. And um, and the idea is that we do have models that simulate the monsoon pretty well. And those are state-of-the-art climate models. And I show here the answerable mean for semi-5 models and semi-6 models compared to the observation. And you can see that those models are getting better. I would say they're starting to be fairly good at simulating the monsoon, even if the patterns are not exactly as observed. They tend to be a little smoother and less intense than what we can see in the observations. But overall, they are doing a fair job, and that they are getting better. And that's notwithstanding with the fact that we are going to get very soon global kilometer scale or kilometer resolution models. So far, we can get very long simulations with those models. There is an intercomparison project that's called Diamond 3. A lot of you are familiar with it. And the project is essentially to produce a 1 year simulation with a kilometer scale model. So we're far from getting, well, we're not quite there to getting climate projections with this type of resolution, but still with our like 100 kilometer resolution uh, general circulation models, we do get a fair representation of the monsoon. And so if we want to do projections, climate projections, or if you want to just do some slide to get some results about the monsoon by simulating it, we do have the tools. When we are interested in simpler modeling of the monsoon, and by that I mean intermediate complexity or very simple models of the monsoon, it's more about understanding what the mechanisms of the monsoon are. So it's nice to be able to simulate it very precisely, but it's not by simulating that you get an understanding of how things happen. So you can do some kind of experiment with climate models, but most of the time you will have to simplify or remove a mechanism to be able to assess how much that mechanism brings to the monsoon. And so here I'm going to try to present the different models that have been used in the past to try to understand some aspects of the monsoon. And I try to show kind of what the simplest models would give. And if you get it in a simple model, you should be able to get it in every more complex model that you get all the way to DTMs. And that's actually something that's important. I'll get back to it. But if you find something in a simple model or in an intermediate complexity model, it's hard to know exactly if this is model specific or whether you actually have found something. So using a hierarchy of model is actually important together with observation analysis to ascertain if what you find in simple models or in intermediate complexity models is realistic. So I'm going to go from the simplest to the more complex. In a way, the simplest idea on the monsoon, even if it's not quite well, depends how you describe it, but the simplest image of the monsoon is that of a giant sea breeze. So some would say, okay, so we have hot land surfaces and air rises over hot surfaces. the breeze comes from the sea. And this way we have an overturning circulation. So that's a very simplistic vision. And especially if we see in this, the second image here, this giant sea breeze image is really limited in terms of how it represents water and energy cycle. Doesn't have any zonal circulation, essentially. It's all meridional and vertical. Zonal asymmetries are completely ignored. And why would the sea breeze become giant? So go over the essentially 100 kilometers scale that a sea breeze will affect. Um, that's that's really not explained at all. But if you think of, we do have an overturning circulation with part of it that's powered by the differential heating of oceanic and land surfaces. And that's powered not only by the heating at the surface, but also by the retroaction or the feedback of cloud convection over the hot surfaces. Then you're getting to sort of giant sea breeze that does have something to do with the monsoon. So what do we need to get to this minimal model? Well, you see that we need to do a lot of um, of approximations. And the first step is essentially to get to a sort of two-layer model that would allow that type of overturning circulation. And the best way to do that is probably to follow the path that's taken for the quasi-equilibrium tropical circulation model, although in an even simpler way. So if you assume that your temperature profile in the atmosphere follows a fixed perturbation profile that also is the same as the cloud latent and radiated heating profile, you can compute the profile of zero potential that is a result from the hydrostatic equation and this temperature profile. And then if you assume then that the horizontal wind follows this profile, then you also have a profile for your wind. And so you can actually resolve this all the primitive equations with just that degree of liberty of the temperature anomaly. So that's called T1, which is the amplitude of the anomaly that depends on horizontal coordinates and time. And then everything on the vertical is actually compressed into that reference deviation profile. When you do that, you still have two dynamical modes. One that's homogeneous on the vertical, that's the barotropic mode. Then you'll have a first baroclinic component that is going one way in the upper troposphere and the other way in the lower troposphere, and with vertical integral is zero. But then, because the barotropic component, if you consider that you have a fixed surface and a fixed top, the divergence of the barotropic component has to be zero, means that the barotropic component will be only rotational, and you can actually neglect it in some cases. And so you can actually get back to just one vertical mode, one first baroclinic mode on the vertical. But it's also an additional hypothesis that we're doing here. And so that gives you a first baroclinic model, which is very popular. That's essentially the one that's studied in dynamics since the earlier days of the 60s. So when you think of Matsuno's work or Gilles' work on waves or damped waves, forced and damped waves, then that's exactly the type of system that they're looking at or they're thinking of when they're analyzing the shallow water equation. So this is what you will get in terms of a first baroclinic model. So you get one mode for wind, one energy equation that's for the column energy budget, one equation that's for the column water budget, and you can combine those two into a budget for the most static energy of the column. And you can see that we have like here in the energy budget, we have the horizontal advection and the vertical advection, and of course the diabatic heating Q1 here, that are going to determine the tendency of temperature. And so this vertical advection, there is that factor here, that's the dry static stability. So it's the amount of energy that's exported from the column for a unit of divergence of the horizontal first baroclinic wind, which means that it's the amount of energy that's exported by unit mass of the overturning circulation. If we have ascent, and if you had descent, is the amount of energy that is exported by the overturning circulation. And in the same way, but we usually take it the opposite here. You have a minus. So this MQ1 here is the moisture stratification, which is the equivalent of MS1, the dry static stability for humidity. And it's taken to be with the opposite sign just so that the parameter is positive. So this parameter MQ1 or variable MQ1 is the moisture stratification, which is essentially the amount of latent heat or humidity that is imported into the column by the vertical circulation, or by ascending, by unit of ascending circulation. So if you have convergence in the lower troposphere and divergence in the upper troposphere, you are, with MS1 positive and MQ1 positive, you are exporting energy and importing humidity. And of course, what appears in the moist static energy budget is this M1 is the moist static stability, which is the amount of moist static energy that is exported per unit mass of ascending motion in the column. And so it's, the dry static energy that's exported minus the latent energy that's imported. And both, so by when you look at the tropical atmosphere on Earth, you've got MS1, so the dry static stability that's positive, MQ1, the moisture stratification, that's positive as well, and then about the same order of magnitude, which means that M1 is going to be the difference between the two. It's going to be much smaller than each one of them. And in average, over the long term, over the tropics, M1 is slightly positive. But when you look at, for example, tropical variability, often in the development phase of a convective perturbation, M1 will be negative and then become positive and more so during the mature stage of this convective perturbation. All right, so let's get back to our minimal model. So if we have those first baroclinic equation to try to get even simpler, then we can simplify the geometry. So if we neglect the variability in the horizontal direction, then that's what we call the axis symmetric configuration. So you can still have zonal wind, but you don't have any variability in the zonal direction. And so variables are the same all over the globe, essentially along for all longitudes, they're the same. And that's a configuration that you can apply, of course, to this very simple model, but also to more complex models. And we've done it a lot in the past. And I show that for intermediate complexity and even general circulation models a little later. Then you can limit the median variability to 2 points. So then you get a box model. So for example, here, what I'm showing is such a model where you have a point over the ocean and a point over the continent. And so what you're interested in is just the circulation between those two boxes. And then if you neglect either rotation or motion in the zonal direction, then you remove all circulation that's perpendicular to that plane of this schematic here. And then you get a model that's essentially looking at a giant sea breeze without imposing too much of a horizontal scale, etc., etc. Oh yeah, by the way, this last assumption here or simplification is actually completely necessary, even if it's been done very regularly. If you just take an F-plane approximation, you would get the same results, except that if you take just a damping term, a simple Rayleigh damping term in the momentum equation, that damping term would be modified by a function of f, but otherwise it would be exactly the same type of results that you would get. So in a way, this last simplification is unnecessary, but it was done in the models that were used in the literature. And so with that, I think this is really the minimal model of monsoon that we can use. It does match that giant sea breeze image, but with a basis that's much more physical than just, oh, we've got the land that's heating, though, so air is rising and converging onto lands due to that heating. We actually get six fairly drastic simplifications, but they're somewhat physically based, and we know which ones they are. And it's not that this type of model is you can do a lot with them. You cannot do that much with them, but you can do at least a little with whether to investigate whether there's a monsoon at all. And there was quite a bit of a debate about that around 2015, 2016. In particular, there was a paper by Leverman et al. In 2009 that was suggesting that there could be abrupt changes in the monsoon. And there was a paper by Busan and Stolevmo to try to show that this wasn't quite the case. And it comes from the fact that in the paleo climate report, there are cases when there was clearly a much weaker or almost no monsoon at all. So essentially the idea is if you have such a box model on the monsoon, do you have precipitation over land, like here on the left, and low level wind from the ocean box to the land box? Or do you have precipitation over the ocean and the low level flux goes from the continental box to the ocean box, and then you have no precipitation or very little precipitation over land? And the answer to that question of whether we can have abrupt transition or abrupt disappearing of the monsoon due to maybe paleoclimate conditions or maybe due to climate change, that's a little bit what Leverman was going after. Well, I think Booth and Sprovelmo actually gave a very convincing answer, where they said essentially the energy input in the atmospheric column either over is larger over ocean than over land, then we'll have precipitation over the ocean. And if it's larger over land than over ocean, then we'll have precipitation over the continent. And that's essentially relying on the fact that the gross moist stability is large enough. So if the dry static stability is large enough, then the gross moist stability will be large enough. And then for any convergence of for any input of energy over land larger than over the ocean, then we'll have a circulation that essentially exports this energy to the reservoirs. And this circulation will be with ascent over land, and then we'll get the monsoon. So that's what's shown by this little diagram here, where you have the low level wind pointed positive towards the continent, and the precipitation in blue for a positive value of the gross moist stability. And you can see that you have a monsoon as soon as you have essentially energy input into the atmospheric column over land. So they also looked at what you would need to actually get a sort of abrupt transition and maybe a hysteresis. And that's what's shown by the dashed blue line here. If you take a gross moist stability equals to 0, then you actually can get an abrupt transition because of the monsoon, because you get a hysteresis. Essentially, you have the equilibrium that you can see here in solid blue does exist for energy export from the column, just because then you can have horizontal transport and other processes that can maintain the monsoon over land, even if you have export of energy from the atmospheric column. That's because the vertical transport of energy isn't the dominant transport of energy anymore. And so you'll be able to have sometimes, if you go beyond this threshold, to have an abrupt transition towards a regime without monsoon. And in this case, you could explain maybe why the monsoon collapsed in some paleoclimates. But in the current climate, the gross moist stability is positive, just because the dry static stability is large enough to compensate the moisture stratification. And so we're not expecting that to change that much. Although when we look at how positive the gross moist stability is, it's actually not that large. You can see Oishi Chakraborty's poster about energy transport in the tropics. And it's a little more complex than this simple, slightly positive gross moist stability associated with the first barocclinic mode idea that is the fundamental base of this result by Booth and Sorel mode. So that's what we can get with the minimal model. The giant sea breeze idea gives you just essentially one thing, is that whether the monsoon will exist or whether it will collapse. Essentially, that's the fundamental result that we can get with this type of model. So now if you go to slightly more complex, we get into the range of intermediate complexity models. And essentially, historically, we've had this the type of model that has been developed is not models with very simplified physics. The main simplification that was applied was to simplify the vertical structure of the atmosphere. And so, for example, Webster and Shaw in 1980 proposed a two-layer model, which is shown by this schematic here. So essentially, considering in the atmosphere, one layer for the upper troposphere and one layer for the lower troposphere. And they also couple that with a simplified model of ocean with a oceanic mixed layer and a deep ocean. And then you've got what I will call a 2.5 layer models, which were first proposed by Wang and Li. So essentially, in this type of models, you've got also two layers but for the free troposphere this time, not for the whole troposphere. And then below that, you'll have a boundary layer. But we consider that this boundary layer is always adjusted to the coatings around. So it's in quasi-equilibrium with the surface and the free troposphere above. So that's why we call it this one is it's a half layer because it doesn't have any pronostic variables in it. It's just always well adjusted to the rest. That's the first way. So you just discretize on a very limited number of layers on the vertical your primitive equation, and you run with it essentially. And those two models were developed only in an axisymmetric version, actually. Then the other approach to simplify the vertical structure of the atmosphere is that one used in a quasi-equilibrium tropical circulation model family. And essentially, instead of considering layers on the vertical, it projects the primitive equation onto a limited number of vertical profiles. So that's essentially a Galerkin truncation. And so I've actually shown you how you can develop a first baroclinic model just using one profile. And in the first generation of QTCM model, QTCM1, so developed by Nilin and Zhang in 2000, well, it was exactly that. One reference profile for the perturbation of temperature and heating. And we can have this way a consistent vertical profile of the horizontal wind. So we get two modes, one barotropic and one baroclinic mode. And then if you want to add moist vortices, you also define a reference profile for the perturbations of humidity from the mean, from the base state. And so that's the first generation of QDCM. So one variable for temperature that gives you the whole profile, one variable for humidity, and two for wind, for the barotropic and baroclinic mode. And this was used in a number of studies for tropical variability beyond monsoon. It's actually a model that's developed over I think a band between 60 south and 60 north, and that works fairly well to represent the tropical climate. The second generation of QTCM, the QTCM2, is essentially the same structure that you have in a QTCM1, but limited to the future troposphere. So you have one profile for the perturbation of temperature, one profile for the perturbation of humidity in the future troposphere, and then two profiles for the horizontal wind in the future troposphere. And then below the future troposphere, you have a well-mixed boundary layer with a well-mixed idea that gives you the profiles of temperature, humidity, and wind in the boundary layer. So you've got one more profile for each of the variable temperature, humidity, and wind in both directions than in the QDCM1. And that model also exists over the globe. It was developed by Lindner et al. And it's been used also in axisymmetric version quite a bit by Tobel and Nilin first, and then I worked on it myself quite a bit with Adam Subel. And so what can you do with such models? Well, there was a big push, a big body of work by Hu and Nilin and some in their groups to look at the northward or the poleward extent of monsoons and what would limit that. And so they were interested in more by American monsoons. So what they used was the QTCM1 over a simplified continent that was essentially covering a band of longitude from all the way north to all the way south. So if you look at here on this map, you've got the ocean on both sides and then a continent in the middle. And they were looking at the factors that would essentially control the poleward extent of the monsoon. Yeah. And with QTCM2 in an axisymmetric version, so with a continent that would go from a given latitude in the tropics that I call YS here, all the way to 60 north or something like that. I was looking at in the axisymmetric QTCM2 what the precipitation field would be. So those are the two tools that could be used to see what controls the poleward extent of the monsoon. And so what we found with this work is that, of course, you have, again, just like in the minimal model, energetic factors that favor or disfavor convection over land. So in the case of this work by Xu et al. In 2001 with the QDCM1, what they did is that they imposed ocean heat transport. And of course, when you look at seasonal scale, your heat storage in land surfaces is very small. So the total heat flux, net heat flux on a continental surface on seasonal time scale is essentially zero. So whatever energy goes into the surface is given back, either on a radiative form or as turbulent surface heat fluxes. So any modification of this budget, or maybe because the land is competing with the ocean for convection, of the budget of the oceanic surface, that's going to impact your precipitation. So in their case, if they don't put any ocean transport, heat transport, then they essentially don't get precipitation over land. When they put oceanic heat transport, what happens is that you have oceanic surfaces that have a loss of energy at the surface on seasonal timescale, while over land, there is a zero net budget at the surface. So the amount of energy that's received by the atmospheric columns over land from the surface is zero, but over the oceanic columns actually lose energy to the ocean because that energy is transported away by oceanic heat transport. So that's very important in the monsoon, and that's the simplest model, I think, where we see it. But we've seen it, although I think that the minimal model could actually include this type of processes. In a way, it wasn't explicitly modeled, but it could be done. And so this is the precipitation and the low level wind that they get in their control simulation with export of heat in the ocean. So you can see that over the tropical land, you get a large scale maximum of precipitation. That's our monsoon there. And down below, you can see what happens if there is no heat transport in the ocean. And you can see that the precipitation moves to settle over the ocean. So there is no monsoon anymore. And essentially what I said a little earlier, where you have ocean heat transport, you have ocean cooling locally, and that disfavors convection compared to land next to it, where the surface net heat flux is zero, and that favors convection there. So that's the first energetic factor that you could see. Now, in the QTCM, axisymmetric QTCM2, I'm showing here the effect of albedo. It's somewhat indirect. So if I tried two different types of vegetation on a continent, I would go down to either the equator or 10 north or 20 north or 30 north. And I compare that with an aquaplanet simulation that's shown in gray here. And so if I have a land surface albedo that's very small, that's a continent covered with forest, and the land albedo is going to be around 0.1. Then I have a precipitation pattern in terms of this dependence with latitude that's essentially similar to the aquaplanet case. But then if I put no vegetation, a desertic continent, with a land surface albedo that's going to be about 0.3, then if my continent goes further south than 20 or even 25 north, then my precipitation pattern starts being significantly different from the aquaplanet. And that's because over land, then we have deficit of the energetic factor. Because when the albedo is high, then it's going to reflect some sunlight. So the surface of the land is not going to get heated as much as for lower albedo. And since there is no storage in the land surface, this is energy that is not given back to the atmosphere through the surface heat fluxes. And so the atmospheric column above a surface with high albedo is going to be disfavored for convection because it's not getting as much energy from the surface. And so that's the second energetic factor that was shown to limit the poleward extent of the precipitation, so the poleward extent of the monsoon. But you can have other factors as well, as long as they impact the energetics. This is the same thing as what we saw in the minimal model. Essentially, the energy input in the atmospheric column is one of the strong constraints on the development of precipitation, so on the development of the monsoon system. But it's not the only one. And it's the one that's essentially associated with this idea of export of moist-static energy by ascending motion. But in the same study, Xu et al. Actually showed that there were other factors, and one of the big ones was something that doesn't apply too much to the Asian monsoon, but definitely applies to the others, including the American monsoon, but also the Australian, the Australasian, and the West African monsoons. What they saw is that you have a combination of a wave that a standing wave, or a stationary wave that develops over the continent, and horizontal advection that they call ventilation, that actually is very important to limit the forward extent of the monsoon. And so the wave that they're talking about is sort of a mechanism that was first proposed to contrast the climate over the Mediterranean and Northern Africa and over India. So it's the Rodwell-Hoskins mechanism, and they postulated that there was a very large-scale wave with ascending motion over the Indian monsoon and descending motion over North Africa and the Mediterranean that would ensure that the Mediterranean gets very dry, and that would link the two climates. So there are some elements of truth that have been, found about this mechanism, but what's been seen also is that it's not completely verified, but we can see some elements of that on much smaller scale. And here, that's something that we can see here. So when you look at the flow, you can see that you have a flow that's bringing cooler oceanic air from the northwest onto the continent, and that's what we call ventilation. So it's bringing cooler air from the ocean, and that contributes also to limiting the forward extent, because this air is too cool to create convection. And since it's coming from the northwest, it's going to give an asymmetry between the east and the west of the continent. And that asymmetry in terms of convection would create a wave, ascending motion over the east of the continent and subsiding motion over the west. That's going to further disfavor convection in the western part of the continent. So that's the kind of Rodwell-Hoskins mechanism, but at smaller scale than that was first postulated by Rodwell and Hoskins. And so these two mechanisms, they limit the northward or the poleward extent of the monsoon. So the ventilation is very clear because it's bringing cool air over the continent, and the Rodwell-Hoskins mechanisms is drying the western part of the continent, which then this dry air is advected back to the region with convection. So that's why we get the monsoon that essentially is moved eastward and even encroaches over the oceanic region. And if you remove the horizontal advection from the model, as is shown here, then you get a very different pattern for precipitation, because the horizontal advection is not only affecting ventilation over the continent, but also other aspects of the model. But what you can see for the monsoon part is that your precipitation is going to expand northward or poleward if you remove this atmospheric advection. So that tends to show that the ventilation mechanism is important. And then the third mechanism is the soil moisture feedback, and that's something that Webster and Shaw had already kind of pointed out. That if you look at your mean circulation, you still have reduced soil moisture in the subtropics over land and over the ocean. You have a drier boundary layer. because of subtropical descent. And so that will also limit the forward extent of the monsoon just because the moisture availability in the subtropics is not sufficient. And same thing, if you impose the soil to be saturated over land, as is shown in this panel here, then your monsoon will be much more extended forward. One very interesting aspect that was tackled with this type of models, mostly with axisymmetric models, so either in the Wang and Lee model or the QDCM, mostly QDCM2 models, but also in the Western shower model, and particularly by people from the Indian Institute of Science, that you can see here. This is the poleward propagating monsoon intra-seasonal oscillation problem. And I think you're familiar with it, but I just sum up its characteristics. So you've probably seen that last week. But essentially what it is, this oscillation is what's happening in the boreal summer to the Madden-Julian oscillation. And instead of propagating just eastward, it propagates northward. And it develops in the equatorial Indian Ocean, grows and then propagates northward over the south of Asia. And the time scale of this mode is essentially the pseudo period is about 40 days. And so each phase that I'm showing here is about 5 days long. And of course, you have the circulation that's essentially in quasi-equilibrium that is associated to this anomalous convection. Now, if you look at the meridional and vertical structure of this mode, that's something that Jiang in 2004 did, and I've redone it here for you. So you can see the Euler and precipitation up here, and then the composite humidity that's associated to that in terms of latitude with respect to the center of convection and vertical coordinates. And here the divergence, and here the vorticity. And you can see that ahead of the maximum of convection, you have a maximum of humidity, and particularly in the lower troposphere, it's even further north. So what's happening is that the precipitation is moving north because it's more humid, or there's more moisture availability north of the maximum of convection. And that humidity is essentially due to the fact that there is convergence in the lower level ahead of the convection, or north poleward of the convection. And in turn, this divergent pattern is directly produced by a vorticity pattern, because if you look at the divergence equation, there's a term that's essentially f, the Coriolis parameter, multiplied by the vorticity. And so this vorticity pattern is like 4 to 5 degrees ahead of the maximum of convection, or the minimum of OLR. And that's going to create the divergence pattern that you can see here, which is going to essentially transport humidity upwards. And this humidity convergence is going to allow the development of precipitation north of the existing precipitation, and then that causes the northward propagation. And so essentially the idea is that we have to explain why there is this vorticity pattern to explain the northward propagation. And so if you look at the vorticity budget that's here, you've got four terms, four main terms that explain the tendency of vorticity here. First one is the advection of absolute vorticity, if you include here the Coriolis parameter. Then the second one is the stretching. You know, if you have a tube of vorticity, a vertical tube of vorticity, if you stretch it, it rotates faster. And if you compress it, it rotates slower. And then you have the tilting mechanism, which is essentially due to the difference or the gradient of vertical advection. And then you have a dissipation term. And so the first mechanism that was proposed was the vortex tilting mechanism. And so you can imagine that essentially the tilting mechanism is taking an existing vorticity in one direction, and another circulation is moving or is flipping, tilting this vortex. So if you have the seasonal circulation, you have a vertical zonal vortex, and in terms of the zonal circulation, you have vertical shear in the zonal direction. And if you have an anomalous circulation with ascending motion to the south and descending motion to the north, you have another overturning circulation here. And this anomalous circulation can flip or can tilt the seasonal circulation. And that is going to create vorticity in the horizontal direction, right? So you have a vertical zonal circulation that's tilted by a vertical meridional circulation, and that gives you a horizontal rotational circulation. So that's the mechanism that was proposed by Zhang et al. On the basis of a Wang and Li 2.5 layer model. And the other mechanism was what I proposed with Adam Sobel in 2008 paper, which essentially says that the advection plays a role in this propagation. What's interesting is that essentially what happens is that the meridional overturning circulation is going to advect vorticity anomalies at the top of the atmosphere and at the bottom of the atmosphere in opposite direction. But around the perturbation of convection, the anomalous circulation is rotational in opposite direction at the top and at the bottom of the atmosphere. So the seasonal circulation is going to advect anomalies of opposite signs in opposite directions at the top and the bottom of the atmosphere. That creates vorticity that has the same sign over the whole atmospheric column, whole one of the maximum of convection. And that explains this pattern of vorticity and the northward propagation. And that's the type of result I would get into the full model thanks to this mechanism here. So this is result from the axisymmetric QTCM2. It's just the Hofmöller of precipitation anomalies as a function of latitude with the equator right here. And you can see very regular propagation. So another question that was interesting to tackle with that is what is the role of coupling with the ocean? Because in a lot of models, we had seen at the time that the topple model would produce better, essentially, intraseasonal variability overall, but in particular the monsoon intraseasonal oscillation than the atmosphere-only model. And so coupling this axisymmetric QTCM2 with a simple 1D ocean model was a way to try to figure out what the role of the coupling could be. And so you can see that in the atmosphere only model here and the coupled ocean atmosphere model, we have oscillations with about the same structure. The main thing that changes is the period of this mode, right? It seems that the period is shorter in the coupled ocean atmosphere model. It's about 20% shorter, actually. We go from something like 40, 42 days to about 35 days. And when you look at this in this coupled model, of course, you have an SST anomaly. Now you can see that essentially the SST anomaly is positive north of the precipitation and negative south of it. And so that's why the coupling accelerates the poleward propagation, right? Because the SST is larger poleward or higher, warmer poleward of the convection. And that's just from surface sensible and latent heat fluxes, which are both for the sensible and the latent, a function of SST to the saturated humidity for the latent. And so if you look at the tendency of moist static energy in the boundary layer that I write HB here, there will be a term due to the surface heat fluxes that's proportional to the perturbation of humidity if you just linearize it. Sorry, the perturbation of sea surface temperature. And so what happened essentially is what I put is on this diagram here, where you have positive SST anomalies forward of the convection that creates positive anomalies of surface heat fluxes, and the opposite south of the convection anomaly. So that tends to favor the poleward propagation of the convection. Since there is already an existing poleward propagation, it accelerates it. So that's about it for intermediate complexity models. And I don't have that much time left. I just wanted to point out that the next level of complexity is essentially using primitive equation models or general circulation models, but in an idealized configuration. So you have just configurations with no continents. I think that's something that we saw quite a bit in the last school. But you have this tradition of simulations without any moist thermodynamics, whether it's an axisymmetric model or just a full GCM. But instead of having all the thermodynamics, we just have a relaxation of the temperature towards sort of equilibrium profile. That's what we have in Held and Howe, for example, or subsequent work that address more the Monsoon, like Leibniz and Howe, Planck and Howe, etc., etc. And so at first we have that axisymmetric view with no ADs. In that case, thanks to the High theorem, we have an angular momentum conserving Hadley circulation. And we had all this work on the fact that the maximum of temperature or maximum of heating was off equatorial would make the intensity of the circulation much stronger than if you had something symmetric about the equator. Although there is some time necessary to adjust to equilibrium. So when you look at equilibrium circulation, it seems to be the case. It's less clear when you have just a seasonally varying equilibrium temperature or heating. Now, with the work of Walker and Snyder, that was put into question because of the role of eddies, right? They use a dry model, but not axisymmetric. So they could see that the eddies are very important to the Hadley circulation. Although during the monsoon, that's the moment where the circulation is closer to the angular momentum conserving regime. And so you also have a whole tradition of models that are axisymmetric, but with moist thermodynamic. And that complexifies things quite a bit. For example, some of the moist thermodynamic processes can actually produce very high sensitivity of the circulation to the amplitude of off-equatorial forcing. And so wind-driven surface heat fluxes or moist convection can both do that. And that can create that nonlinearity that could explain why the onset of the monsoon is very fast. And then you have also aquaplanet studies, which Simona Bordoni with collaborators has done extensively. And the first big result of that was that the monsoon onset could be seen as a rapid transition between these two regimes, like an eddy-dominated regime and another regime that's closer to the angular momentum conserving regime. So this debate of the Hadley circulation, eddy-driven or eddy-dominated versus angular momentum conserving, we have this debate too in terms of the monsoon, so the asymmetric Hadley circulation. And the next level is configurations of general circulation models, but we idealize continents rather than no continents at all. And so you've got axisymmetric versions, and mostly the idea at that point was to look at the difference between axisymmetric versions and non-axisymmetric versions. And you've got some work by Privé and Plum, and then some work by Perry and Lafort, but very focused on the African monsoons, that show how the eddies do impact these circulations, but then the existence of a continent does influence that, and we have also the problem of ventilation that's much stronger, and essentially all zonal transport become important. That's what Perry and Lafort found in the case of the African monsoon. But also what Plumbé and other zonally symmetric continents, then your simulation is somewhat close to the axisymmetric solution. What changes really is when your continent is not zonally symmetric. Then you have a lot of those zonal influences that come into play. And of course, the next level of complexity before we get to the full realistic continents is just rectangular continents. So that's when you have a zonally varying surface condition, and when you have ventilation and zonal transport, that becomes somewhat important. So in the case of the Asian monsoon, these zonal effects are still not that well understood, and they're very complex because part of them are blocked by the mountain ranges of the Himalayas. So some of them still exist coming through the Hindu Kush region, but somewhat modulated by this orography. And that's all I wanted to say today. So those simplified models compared to state-of-the-art climate models are a good opportunity to test ideas. The problem is that in some cases, like we've seen in the axisymmetric cases, some of the mechanism might be due to an oversimplification somewhere. So let's say, take the example of the Hadley circulation. As long as we had only axisymmetric models, we certainly could not assess the role of eddies. And once we went to the next step with zonally varying circulation, we realized that the eddies were actually crucial to any Hadley circulation, either symmetric or asymmetric with respect to the equator. So it's important when you use simplified models to use a hierarchy of models and to go back to observations, or to start with observations and go back to observations after your work. And that's it from me today. Sorry, I was a little long.
Thanks for the very comprehensive overview of the hierarchy of models. Questions?
Can you hear me?
Yes.
Yeah, I'm Sambrito. So we also had this discussion a couple of years back. So for the intraseasonal oscillation part, you have shown what you have got in model. You have shown the structure of the moisture and the vorticity and the divergence. So I agree with the vorticity part of it, but if you just add a moisture tendency structure also with it, you will see that the divergence is not actually playing any role there. So it's totally advection. In fact, where you have the moisture tendency, strongest moisture tendency, positive moisture tendency, there we would have moisture divergence rather than moisture convergence. So tilting and the vorticity argument of course holds, but not via divergence, but via moisture advection at lower free troposphere, just like the moisture mode.
So, yeah. So, I mean, this is true. This is very true in over the Bay of Bengal, where you have horizontal advection that's very significant. Now, if you look at the so yeah, so this is a little.
Huge.
So when you look at essentially the early phases of the development over the Bay of Bengal, then the circulation over the Bay of Bengal. So you've shown that, right, in your paper, is very significant. But what's interesting is that when you look at the longer tail over kind of the maritime continents, and then over the Western Pacific, it's much less the case. So there the vertical, I mean, the moisture convergence is a significant factor. And so when you kind of compose it over the whole mode, then you have a little less of an impact of the horizontal advection of moisture. But yes, actually that's something we're working on with Vishal. Like, what we're looking most so far, we're looking at the only the vorticity budget, but we want one day to get to the moisture budget with the same type of methodology. You do have in the Bay of Bengal also effects that are kind of due to the horizontal advection in the zonal direction on vorticity. So yeah, when you look at the western part of this mode, there is a lot more horizontal advection, more role of the horizontal advection, both for vorticity and for moisture.
Since you have this slide up, I have a question regarding the vorticity structure that you observe. So you see that the cyclonic vorticity anomaly is quite deep. How much of it can you explain from like the structure of the meridional wind, because you said that advection plays a key role. So how much of that can you explain solely from the advection, and how much can you explain from stretching? And where does tilting kind of come in?
So, so I mean, you even in the model, in the work that I did, there was some role of the tilting in the full model. The what was interesting is that the one thing that was really important for the propagation and the instability was the advection. But then for the full structure, the other was, well, the tilting was important too. And what Vishal found was that both were important in his model. In fact, when you do the vorticity budget, what you see is that the advection is very important for really the lower troposphere. And also the very upper troposphere, but it's almost in the stratosphere. It's really narrow. So it's really at the top and the bottom that the advection is going to be important. Well, the tilting mechanism is going to be in the mid-troposphere. And so when you see the vorticity pattern here, so the maximum that you see at the bottom here, well, in the lower troposphere, this is really mostly advection. But then in the middle here, what you'll have is something that's caused by tilting for most of it. So you really see those two mechanisms working together in the vorticity budget in the reanalysis.
Okay, so just as a follow-up, so you don't see the effect of stretching as much, because you do have like a strong low-level convergence, right?
Yes, but we don't see a very strong role of stretching.
Okay, thank you.
Thanks, Gilles, for a nice talk. Gilles, can you make a comment about how we could use these models, intermediate complexity or simplified models, to really diagnose errors in either traditional climate models or the upcoming machine learning models, machine learning based weather and climate models?
Well, I don't see. So I think what's interesting is to get ideas from intermediate complexity or simple model. So if you get an idea of a mechanism of something that's important, and you can show in an intermediate model that it is the case, and you can check that in more complex models it seems to be verified, and then you can have a metric for this particular mechanism, or maybe different potential mechanisms. Then you build a metric that allows to attribute essentially a role to the different mechanisms, and then you can apply this metric to the observations, which allows you to show which mechanisms are actually significant in real life or in the real world, and then you can use these metrics to diagnose the climate models. I think that's the main, the main contribution of simplified models to the evaluation of big models. Yeah. Is really identifying the mechanisms, but then from that you have to be able to go to a more realistic situation. So you have to build a metric or some kind of tools that relies on your understanding that you get from the simple model, but you can't directly compare simple models to state of the art or current climate models.
Yeah, maybe a follow-up on that. So your first slide showed CMIP 5, CMIP 6 and observations. And I was thinking CMIP 6 was better than CMIP 5. Uh, so is it just that the higher resolution resolved orography better, or you think that any of the mechanisms such as say representation of shear, either zonal or meridional, as well as some of the mean profiles of vertical heating, as you show in your first part of the talk, that is the key building block for QTCM. What may have really improved in CMIP 6 versus CMIP 5?
I think there is some contribution of resolution, but not that much. I think it's models are getting better. And they're getting better in different respects, right? I mean, depending on the models. You can have some got a better representation of deep convection, better parameterization of deep convection. Some other models just got a better representation of shallow convection. I mean, each modeling group will improve a few things between two generations of models and not that much more. But they're different from group to group. I do think, it's mostly in the thermodynamics and surface parameterizations that are in play here. And you can see that some things are not well captured here. Then you can see that in terms of resolution and how the orography is represented, you can see over the Western Ghats that you don't have the mountain slope that are sufficient to create the rain band that's observed, and then you get something that's a little wider and not as intense. So I guess that's something that orography, higher resolution for orography will help, and as now, but I do think overall the models do improve. And it's hard to ascribe when you look at an ensemble mean like this. It's really hard to ascribe the progress to any one of or a handful of factors.
Yeah, sure. Yeah, thanks a lot, Gilles.
Thank you. I have a question for you. When you show those composites phase 1 to phase 8, are the biweekly modes included there, or they're left out by design?
They kind of filter out because this type of what is it? Yeah, because the two first AOX of the subseasonal anomaly are really this mode. So this is built on extended EOX and extended EOX of OLR. That's Kikuchi's method. And so if you just pick up the two first EOX, then you don't have the quasi biweekly mode represented.
What are the types? Are they all
The quasi-briefly mode would be represented by the next EOX, and they're somewhat smaller. I think the problem to get the quasi biweekly mode would be to have a smaller window in a way, in terms of smaller geographic window, because it's a little less large scale. So when you do the analysis over the very large scale, you end up only catching this forward propagating 40-day mode.
All right. Thank you.
Okay, so let's thank Gilles again.